Good evening, everyone. My name is Saida Said. I'm second year research scholar, third year research scholar at IIT Roorkee, and this is our 12th interactive session and the final interactive session for this course, Geotechnical Engineering 2. And in this final session, we will be talking about questions based on uh, machine foundations, because that was the last topic which we have not covered in our lectures. So, okay, let's go. So, the exciting force of a machine is 100 kilonewton. Determine the transmitted force if the natural frequency of the machine foundation is 3 Hz. Take D equal to 0.4 and the operating frequency equal to 5 Hz. So, let's solve this. So, what is given to us? Let's just write that. D equals 0.40, which is given 5 and 3, and we have also been given the exciting force, which is F naught. We need to calculate the transmitted force, Ft. So the formula goes okay. M is the moment. So if we calculate the moment equals 1 over 1 minus r square plus 4 d square r square root, which will be 1 over 1 minus 5 by 3 square square plus 4 into 0.4 square into 5 by 3 square. So let's calculate this. We will get 0.45. Here Ft is F naught M 1 plus 2 dr square. We will get 100 times 0.45 times square root 1 plus 2 into 0.4 into 5 by 3 square. So let's calculate. We will get the transmitted load of we will get 75 kilonewton. Okay, so let's move on to the next question. So the next question, so this was a pretty simple question. Next question, we will be talking about a cyclic plate load test. Let me mention here. So a cyclic plate load test was carried out on a deposit of silty sand to estimate the elastic coefficients for the design of a compressor foundation. The test was carried out at a depth of 3 meters using a 30 centimeter test plate. The data obtained was it means I'll insert a table as given below. Plot the stress versus elastic settlement relationship and determine the values of Cu, Cr and C phi. Okay. For 10 meter square base area. Okay, so let me give you the values. So okay, this is the load intensity, given in kilonewton per meter square, and then we have the settlement given in mm. 25, 0, 50, 0, 5, 0, 100, oh, 100, 150, 250. Okay. Excuse me. 0, 150, 0, 200, 0, 250. Oh, one more. 0. Let me reduce the size so that it fits in our page. Okay. Now for the settlement, this is 0 0.5, 0 0.4, 0 0.95, 0 0.8, 1.6, 1.25, 2.5, 1.9, 3.6, 2.6, 4.8, 3.8, 6.7, and 4.9. Okay. So let's proceed to solve this question. So from this data, what we can do, from the given data, what we can do is we can calculate the elastic settlement as the difference between these values at a particular loading for a particular load. So let's do that. Let me insert another table. This will be okay. Okay. So for 25 kilonewton per meter square, we will have an elastic settlement. Let me write elastic. We will have an elastic settlement of 0.1. For 50 kilonewton per meter square, we will have an elastic settlement of 0.15. 0.95 minus 0.8. For 75 kilonewton per meter square, we'll have a settlement of 1.6 minus 1.25, which will be 0.35. For 100 kilonewton per meter square, we will have 2.5 minus 1.9, which is 0.6. For 150, we will have 3.6 minus 2.6, which is 1. For 200, we will have 4.8 minus 3.8, which is 1 again. And for 250, we will have 6.7 minus 4.9, which is 1.8. So these are the values of elastic settlement for different load entities. Moving further, if we plot the load intensity P versus elastic settlement, I want to plot this in Excel, but then I won't be able to share my screen. So let me see how I can do that. Okay, let me plot this in Excel. Just give me a moment. So my Excel is loading. One second. Let me see if I can add. Mm, I hope you can see this. Okay, and if I do this, okay, fine. So I hope you can see my Excel window now. So let's try to plot this graph, which we just uh, were talking about. So the load was 25, 50, 75, 100, 150, 200, and 250. Then we have the settlement in millimeters. Settlement, elastic settlement was 0 0.1, 0 0.15, 0 0.35, 0 0.6, 1, 1, and 1.8. Okay, so let us draw a graph for this. Let's draw a plot for this. The x-axis, we will draw elastic settlement, the y-axis we will draw the load. Okay, we can the axis titles, this is the load, there's the settlement. So what we can do, we can include a trend line that almost goes through most of the uh, points. Let me change the limit here. Okay, let me also fix the intercept from 0. Excuse me. Okay, and we display the equation between the load and settlement. Excuse me. Okay, actually let me change this chart type to this. So this is a better representation. So we can see this in a better way. And now after plotting this, we get the slope of this plot. The slope will be, let me calculate here, 155.73 m. This is the m, 155.73. So we can write it as let's do one thing first. We can do one thing, we can convert this into meter so that we get in MKS. Let me take a row here, this divided by 1000. and then we can plot this. And then we'll have axis options. Okay, so we get 155. We can write 1.5 into 10 to power 1, 2, 3, 4, 5 kilonewton per meter square. Kilonewton per meter cube. So the area of the plate used is, if we go here, let me actually copy this. Okay, so this will be our settlement curve. So the area of the plate used is 0.3 into 0.3, 0.09 meter square. Thus, for 10 meter square, base area CU equals 15 into 10 to the power 4 square root 0.09 over 10. So let's calculate this. And this comes out to be 1.42 into 10 to the power 4 kilonewton per meter cube. Okay, now C top equals half of Cu, which is half of 1.42 into 10 to the power 4. This comes out to be 7.1 into 10 to the power 3 kilonewton per meter cube. And let's calculate the C5. Now C5 will be equal to 1.73 into 1.42 into 10 to the power 4, which will be 2.46 into 10 to the power 4 kilonewton per meter cube. So that is about this question. Now let us try to solve another question. Okay. The following data refers to a vertical resonance test carried out on a 1.5 meter into 0.75 meter into 0.70 meter high concrete block for estimating dynamic elastic constants for the design. Let me rescale this. For the design of a forge hammer foundation. The test was carried out at a depth of 6 meters below the ground surface. The soil at the site was clay of low to intermediate compressibility. The weight of oscillator motor is 2.1 kilonewton. Draw the amplitude frequency plot and determine the value of Cu, C tau and C5 for 10 meter square base area if the weight of the block and oscillator assembly is 22 kilonewton and maximum dynamic force of the oscillator with an eccentricity theta of 140 degree at 5 Hertz frequency is 5 kilonewton. Determine the damping factor. First, let me actually uh, refine the text. So we have a C file, we have a C tau, and we have this multiplication sign here. We have a square here. Okay, we also have a theta here. Okay, 140 degrees. So this is the question. Let us move forward and try to solve this. Okay, I also have to give you the table with the data. So let me give you that. 1, 2, 3, 4, 5, 6. So we have frequency, cycles per second, and we have amplitude in mm. This is 20, 25, 30, 35, 40, and 45. The amplitude is 0.018, 0.030, 0.068, 0.120, 0.138, 0.130. Oh, 0.138. Okay, so this is the data given to us. Let's first draw the frequency amplitude plot. Let's draw the frequency amplitude plot first. So first let's draw the frequency versus amplitude graph. Okay, let me draw this again. So our frequency in cycles per second is 20, 25, oh, 30, 35, 40 and 45, and our amplitude is 0.018, 0.03, 0.068, 0.12, 0.138 and 0.13. Okay, so let's draw. X will be our frequency and Y will be our amplitude. No, I have to switch the frequency and amplitude. Did I do something wrong? Okay. This is not 18. This is 0.018. Okay, that's better. Okay. So this is our amplitude. Mm. This is our frequency. So this is our graph. So that was the first part of the question. We had to draw an amplitude versus frequency versus amplitude graph. Now let's move on to the second part. Draw the amplitude frequency plot and determine the. Now we have to determine Cu, C tau and C phi. Let's do that. From this plot we can see the natural frequency if we magnify it a little, somewhere here we will get the natural frequency. Let's take the natural frequency at 43. Okay, so from the plot, natural frequency can be taken as 43 cps. Assuming the unit weight of concrete as 24 kilonewton per meter cube, the weight of the block will be 1.5 into 0.75 into 0.7 into 24. This will be equal to 18.9 kilonewton. Now weight of the block plus oscillator and motor equals 18.9 plus 2.1. This comes out to be 21 kilonewton. Now contact area of the block, excuse me for a moment. Okay, now the contact area of the block is 1.5 into 0.75 into 1.125 So Cu will be 4 pi square F nz square m by A. This will be 4 pi square 43 square 21 over 1.125. Nine point 81. To convert the kilonewton, we divide by 9.81. This will be equal to this comes out to be 13.9 into 10 to power 4 kilonewton per meter cube, or